just take this AJJ element. Let's say it has a value x. Okay, it has a value x. Because the row sums up to 1, it must be the case that the remainder, these other guys here, they sum up to 1 minus x, okay, in magnitude. Okay, that's the circle theorem, right? We just did that last time. So where do the eigenvalues lie? So I have some point over here, and I'll call that x, and all the eigenvalues must lie in a circle of radius 1 minus x. Okay, somewhere. What is the largest magnitude eigenvalue that you can have? Well, it's going to be something, okay, it's the magnitude is this distance over here. Like that. That's the distance from the origin. That's the magnitude. So intuitively, it's clear that the largest magnitude happens when this kind of swings all the way down over there, tangentially to that point, right? Otherwise, it's going to be smaller. Just think of it geometrically. I have this arm, it's going up. Well, obviously, it's going to be shorter. The longest distance is when it's going to be this. But how much is that? Well, this much is x, and this much is 1 minus x. So this whole thing has got to be 1. Right? And so the largest magnitude eigenvalue that you could possibly have is going to be 1. Okay? And we know there is 1 at 1 actually. We know that there's 1 over here, so we can draw an x over there. But everybody else has to be somewhere in this disk, and to the left of 1. And so what did I just said? Every eigenvalue of A has a magnitude less than or equal to 1. And in fact, we know that this one that's equal to 1 from here. And the rest lie somewhere in this thing. Now we have a bunch of different disks. I didn't tell you which disk, because x could be any value. But it doesn't matter. You know, we have one disk on the first diagonal, another disk here, we have another disk there, whatever. But no matter where the disk is, actually all the disks are going to be tangential to the one. So that's a wrong one. But anyway, the fact still remains that now you can analytically prove this. And if you look at the text, there's a simple proof. It's just a simple maximization, which shows that you've got to have no value that's going to be greater than 1. Okay? So, any questions about this? Okay, so that's where the circle theorem comes in. The circle theorem allows us to very cleanly prove this, because if I'd ask you this question, prove that the largest magnitude eigenvalue of a stochastic matrix is 1, you wouldn't know where to begin. I mean, how do you prove it? You know, it's kind of if I were to ask that question to you a week ago, you wouldn't know where to begin, right? But now you know. You start with the circle theorem, you use this, and then it's actually pretty trivial to prove it. Okay, so this is where it comes in. Yeah.
Since you're saying the matrix and its transpose have the same eigenvalues for all matrix, right?
Right.
So does this circle theorem can be applied to sum of the columns here?
Yes, you can apply that as long as the diagonal elements. So the eigenvalues are going to be the same. You can prove it. Yeah, it will be the same because eigenvalues are the eigenvalues, right? Doesn't. So you apply it. So you're saying does the circle theorem apply to sum of columns as well, right? Yeah. The answer is yes. I think so. Yeah, I don't see why not, because the transpose you can just transpose it, apply the theorem, and it doesn't change it. So you don't need to worry about column or row. Yeah. Okay, so let me continue on here. I'm almost done. So then the next fact we get is that 1 is the dominant, or I should say the principal eigenvalue. And we call it dominant actually, because there may be more than 1. Okay, of A. Why is it the dominant? Because, well, everything else is smaller than that, and that's a definition, so there's nothing new there. And then, and I'm not going to prove this, there's a fact A has only one eigenvalue of 1. Okay, I'm not going to prove it. And so this means that 1 is the principal eigenvalue of A, okay, which implies it's a principal eigenvalue of A transpose as well. Okay, because the matrix and its transpose have the same eigenvalues, this must be true as well. So whatever is shown, all this is just proof that there is going to be a principal eigenvalue of A transpose, which is 1. Okay, good. So far, so good. Now, the interesting part is that let's see what does it mean to have an eigenvalue of 1 for A transpose. Not for A, but for A transpose. Let's just think about the meaning of that, the physical meaning of that. So I have A transpose, okay, and I'm applying it to some probability distribution P, okay. If P is the special probability distribution, we call this P star, okay, which is the eigenvector of A transpose. I haven't told you what it is. Then what is the eigenvalue? Eigenvalue is 1. Lambda equals 1. If lambda equals 1, AX equals lambda x. So the right hand side is what? P star. Okay. So, okay, this is nice. It looks pretty cute. What it says is that the application of A transpose to the probability vector P star doesn't change it. It stays in P star. Okay. So what is the physical interpretation? The interpretation is that once we reach this distribution P star, the application of the transformation doesn't change it. Okay, we can think of it as a fixed point. Okay, it's a fixed point. We keep applying A, it doesn't change. It just stays there and stays there and stays there all the time. Okay, and so this means that the distribution is not changing, and we call that a stationary probability distribution. Okay, it's called a stationary probability distribution, and that's P star over here. And this stationary probability distribution is very, very important because of two facts. First is that once you enter it, you don't leave it. Remember I showed you this absorbing state? The absorbing state said once you enter the state, you never leave, right? It's a black hole. In the same way, P star is like a black hole, except it's not a single state. It's a distribution over the states. Once you enter it, you don't have to leave. You can just stay there. Okay. So that's the first important point. The second important point is that under some conditions, which I will not go into, but we study in queuing theory, but under some conditions we can show that as long as A is stochastic, eventually you'll get to P star. And once you get to P star, you don't leave. So imagine there's this, there's this space, and P star is this point in the space. Okay, it's like gravity. Everything is going to go and then stick to P star. Okay, no matter where you start from, you're going to get to P star. Once you get to P star, you don't leave. Okay, and these are roughly speaking, if A is ergodic. Okay, and I won't explain what ergodic is at all, but again, very roughly speaking, if A has this property of ergodicity, then we have this beautiful result that no matter where you start from, no matter what you started from in the initial distribution, eventually you'll get to the stationary probability distribution. Once you get there, you won't leave. Okay, so a lot of queuing theory is based on first showing that A is ergodic, and second, if it's ergodic, what is the stationary probability distribution? And if you have a stationary probability distribution, the intuitive feeling is that if I sample the state of the system, if I sample it a few times, I'm going to basically be computing the stationary probability distribution. Okay, and so in other words, if I have some set of states, okay, and I don't know what the underlying chain is, it's some kind of chain, whatever it is, and I measure it, let's say, a few 100,000 times, and I can get some kind of distribution, right? I get say, I'm in state 1, I draw a histogram, I'm in state 1 this many times, I'm in state 2 this many times, I'm in state 3 this many times. So this histogram can be viewed approximately as probability by dividing by the number of times you measure. These histogram probabilities correspond essentially to P star. Okay, so if the stochastic matrix is ergodic and we sample it, okay, a few 100,000 times, enough times, then the histogram of state residence probabilities will be corresponding to P star, because once it's there, it's going to stay there, right? So that's basically the beauty of it. So what we do when we do queuing theory is to say, here's a matrix that represents a state. We assume that it's run long enough so that it's forgotten its history. And then the probability in any one of these states corresponds to P star. And I'll show you in a minute. It's easy to compute P star. And once you do this, basically you're done. So then we say, okay, for example, if the Q length in this state is going to be Q1, this state is going to be Q2, this state is going to be Q3, the mean Q length, Q bar, is given by P star 1, Q1 plus P star 2, Q2 plus P star 3, Q3, and that's the mean Q length. So we can talk about the Q length as the mean Q length, and all this depends on the ergodicity. And the ergodicity depends on what? A being Markov. It means that you have forgotten your history when you come into a particular state. So that's the kind of logic over here. Okay. Any questions about this? Yes?
So your claim number 6 that A has only one eigenvalue of 1?
Yeah.
Like what if A is just the identity matrix?
If A is the identity matrix, yeah.
Isn't that going to have all like eigenvalues 1?
Let me see. It would. Let me see. Okay, so we have 1, yeah. So it's all zeros. So clearly it has multiple eigenvalues. They're all 1. I think the okay, so that's clearly stochastic matrix. Okay, so I guess I should. I need to.
Excuse me.
Yeah.
But in this identity matrix,
Yes.
each distribution there is an absorbing state.
Yeah, no, I know. So the thing is that I need to kind of introduce this notion of communicating states and so on and so forth. So right now we have this particular graph. The corresponding graph for this would be looking like this. Okay, etc. Each state is an absorbing state. The conditions under which the stationary probability distribution exists and it's ergodic and so on assumes that basically you can get from every state to every other state. Okay, so this particular fact over here, I did not tell you the conditions under which it's true. And the conditions under which it's true are this notion of communication, okay? And there's actually a few other more technical conditions, something called irreducibility is actually what we call it. So we have irreducibility, we need to have non-periodic states, aperiodicity, and we need to have one more thing which I forget. But if you have all those, then the matrix is going to be ergodic. So I should probably put a fact star on it saying that it's under some conditions that we have this, okay? Otherwise, we have a degenerate situation over here where we can actually just partition it like so, and then each one is a separate chain, okay? And it's not particularly helpful to have that. We'd like to have communication between the states. Okay, any other questions? But yes, technically speaking, what you're saying is absolutely true. And in fact, each subchain would have its own eigenvalue, actually, I would think, yeah. Any other? Yeah. I'm not telling you because there are like 10 different definitions of ergodic. The rough intuitive understanding of ergodicity is that no matter what my initial state is, I'll end up in the stationary distribution. That's so I forget past history. The most intuitive that's the most intuitive definition. Another intuitive definition says that has this notion of a trajectory. The trajectory is basically the path that I took. So I went like this, like that, like that. That's a trajectory. And I can compute the time average of the trajectory, right? I can tell you the probability in a particular trajectory where I am, okay? And the ergodicity says that no matter what the trajectory, right, the time average of being in a particular state is also P star. Okay, and another way is what's called, a third definition is what's called time and space averages. It says I take these trajectories and I compute the, just say in step 1, this is the first trajectory, the second trajectory, third trajectory, I break it up into chunks and look at the probability of being in any state in step 1, in step 2, in step 3, in step 4. I call this the space averages. And another definition is that space average is equal to time average. That's another definition of ergodicity. And each definition of ergodicity has some very subtle meanings. And suffice it to say that you can spend a whole lecture on the 9 different definitions of ergodicity that are out there, and they all argue they're the right place. Everybody thinks their definition is the right one, but they're actually not comparable, as it turns out. Okay, any other questions? Yeah.
I think for other 2x2 matrix, that's 0, 1, 1, 0.
Yeah.
Is there also exceptions?
So 0, 1, 1, 0 is sort of the transpose of the identity matrix.
Yeah.
So then it's not a, yeah, it is stochastic, as we just said. That one is nothing more than 0, 1, 1, 0 is nothing more than 1, 0, 0, 1 transpose, right? Or is that right? No, it's not. Okay. Whoops. This one is stochastic. It's but it does has this property of you don't have this communication property between the subchains. You can kind of break it up. I think, is that right? Let's see. From Z, I always go here. Okay, this becomes what's called a loop. Okay, this is 1, 1. That's what you have over here, right? And when you have this kind of thing, you get into what's called recurring state, okay, which has a periodicity. When you have periodicity, then it doesn't work either, okay? So that's why I said there's some technical conditions of irreducibility and aperiodicity and so on, right? So I didn't want to get into that, but those are the conditions under which we have this fact. So I'm putting a star over here. And if you read the chapter on queuing theory, you'll see the conditions under which those star holds, okay? Right, so for the homework, there are 2 ways of solving it. One of them is to look at this. We look at A transpose P star equals P star, or the normal notation in queuing theory is to use the word pi for it. It's just, that's what they say. Pi is a stationary distribution, and that's what I gave the hint. So this is a linear system of equations, because you can write this down as 0.25, 0.25, 0.5, 0.1, 0.4, 0.5, 0.8, 0.1, 0.1, and this one P1, P2, P3 equals P1, P2, P3. And one easy way to do it is to just multiply everything by 100. So you get the equation 25 P1 plus 10 P2 plus 80 P3 equals 100 P1, etc. And you move P1 over, you get the system of linear equations, and you can solve it. That's one way of doing it. The other way of doing it is to rely on the fact that AT has an eigenvalue of 1, which is the dominant. If you remember from the dominant, that means that we can use the power method to find the eigenvector. Corresponding to this eigenvalue. Okay, so what we do is we just find the, we use the power method, you just find the ratio xtk plus 1 over xtk plus 1 or xtk. If you find this ratio and renormalize at each step, you will eventually find the dominant eigenvector. When you find the dominant eigenvector, that is going to be this one over here. Okay, so there are 2 different ways of solving it. I was going to suggest this, but you could also do this. In any case, if you do it, the matrix you will get will have these 3 values: 0.4117 to 4118, 0.2311, and 0.3571. So, okay, so there are 2 different ways of doing it, but that should be the answer you should be getting. 4118 or 412, 2311, 3571 are the, yeah.
What if it's scaled? It doesn't add up to 102, okay?
Then it's not a probability vector.
But it's still eigenvector, right?
It's an eigenvector, yeah. Yeah, so you can, it's okay. If it's not, yeah. I mean, it's a probability, you add up to 1, so, yeah. By the way, I should add that we have one more equation, which is that actually 4 equations, P1 plus P2 plus P3 equals, in this case, 1, right? So, yeah. So we actually have 4 equations. It turns out when you do this, you'll find that one of them is a linear combination of the other. So you really do need this equation to get the values, but that will be the values that you're going to get. Okay. Any questions about this over here? Okay. So the important part is this one over here, and that's the point of departure for the Google PageRank, and that's one reason why I made you do this homework, which is that if we know that AT has a dominant eigenvalue, then we can just use power method, right? And the eigenvector just pops out. Okay. So the question now is, how can we use this intuition for building a company like Google? So let me talk about that next. Okay. So in fact, those of you who tried the dominant eigenvector, actually you've done a little bit of Google's work already, which is kind of nice. So if you interview there, you can say, yeah, I hand executed or use Maple or something to do this. Okay, so all right, so what does it mean? Let's first understand what is the World Wide Web from a linear algebra perspective. So the World Wide Web consists from this perspective of a bunch of pages, web pages, and we'll just keep it simple. We have some page I, and it has links to other pages, okay? And let's call this J1, J2, J3, and there could be many others, okay? If we have, so, all right. Now what we want to do is that we want to compute a certain metric. We want to compute basically those pages that are good or important as opposed to pages that are not so good. Okay, all right. So what do we mean by page that is good? We mean a page. So let's make a practical example. Let's say I'm looking for the word eigenvalue. That's a search I'm doing. Let's say the word eigenvalue occurs in 1 million pages. It's quite possible it occurs in 1 million pages. When I type the word eigenvalue into my search engine, I want to find the good page which has eigenvalue on it, right? I want to find the good page that's eigenvalue on it. But what does it mean for it to be good? I want to have a rank ordering on pages, on web pages, okay, where rank 1 means it's, or rank, let's say rank A greater than rank B implies that A is a better page. Okay, that's the intuitions. Okay, everybody with me so far? Now, how do we determine something is a good page? Here is what we think about this is the way it works. Let's say that I had J1, J2, J3, a link from page I. Let's say there's some other page over here which links here, and it links to some other pages, and there's some other page over here which links here, and another page over here which links here. Okay, and then this in turn links somewhere else, whatever. Okay, this links somewhere else. Okay, we have essentially a mesh structure, but the important point is this. If I'm over here, then I'm going to this page, and if I'm over here, I'm going to this page, I'm over here, this is going to this page. So the probability of being at this page, okay, if it's a stationary distribution, the probability of being in this page is higher than these other pages, because no matter where I come from, I'm kind of going into this state, okay? And let's say it doesn't link anywhere else. It's a self-absorbing state, okay, page. Then for a moment, what I'll do is I'll convert the web pages into states like this by just drawing circles, and I can view this whole thing as a Markov chain. Okay, it's the same state matrix I drew earlier, it's the same Markov chain I drew earlier, and now what do we see here? If we are entering this particular state, which is this particular page, then we're going to have we're going to stay in the state because if it doesn't point anywhere else. However, the intuition is that the stationary probability distribution of this particular Markov chain is going to correspond to the rank ordering that we want. So if at a particular time I take a sample and I say, okay, where are you going to be? The pages that are highly ranked will have more weight associated with them, okay, because that's a stationary distribution. Another way of looking at it is that when you have, let's just take the very simple example of 3 states, and I'm going like this, and say over here, and that's an absorbing state for now. Each state is giving some importance to this particular state over here. So if I go 0.9 here and 0.1, we can intuitively think that we have probability 0.9, sorry, 0.9, 0.1. We have this probability of kind of going here from here. It's an important site, okay, important state. So I'm going to donate some probability. I'm going to donate my kind of link to here, okay. And in this chain, you'll find, and even if this self loop is, let's say, 0.6, and you're going here with 0.2, whatever, because you have 0.9 of coming in here, chances are pretty good you're going to stay here. Okay, so at a random point in time, the stationary distribution is going to have more probability mass here than compared to these two. And therefore, we will say that this is more important than these two. That's the rank ordering. So the rank ordering of a page on the web can be viewed as nothing more than the stationary probability distribution of the web. Okay. The other way of thinking about it is what's called the random web surfer model. The random web surfer model says that I'm on this page over here, okay, and page I. Let me go back to here, and I have a bunch of links. Okay. So with some probability, I'm going to choose this link or this link or this link. Okay. And if I have k links over here, then probability 1 over k, I'll pick one of those links. I'm just going to go to one of those links, probability 1 over k. And that gives me a probability distribution. And these probabilities sum up to 1. So I get a right stochastic distribution. And I can do it for any chain. So what does the matrix look like? It looks like this. It's a very large matrix. Okay. It has roughly 10 to the 11 rows. Okay. And 10 to the 11 columns. It's a square matrix. And so basically for any entry I and any j, this is the probability of going from I to j for a random web surfer. Okay. So let's think about it some more. So this is page I, and I'm looking at this row over here. Let's say it links to 5 other pages. Okay. Then I'm going to put 0.2 somewhere, 0.2 somewhere, 0.2, 0.2, 0.2, and that's all. The remaining 10 to the 11 minus 5 values are equal to 0. Okay, they're all zeros. I'm not going to go there. It's a very, very, very sparse matrix. It's very large and very sparse. Okay. So that's the probability matrix. What I want to do is to compute now the stationary probability. How do I compute it? Well, I am going to take the power method for a sparse matrix and compute the dominant eigenvector. The dominant eigenvalue is 1, and the corresponding eigenvector is the stationary probability distribution. And that stationary probability distribution is the rank ordering on the web pages. Okay, that's Google. Okay, that's Google. So basically, we give each page a number corresponding to its state ID, and we have this matrix 10 to the 11 by 10 to the 11, which is very, very large. And we just fill up the matrix values with these things, 1 over k. Okay? And then we have the sort of random web surfer model, and then we intuitively, at this point, we just say the stationary probability distribution is the probability that some random web surface on the web is going to come over here, and then we do it. Now there's a little bit more to it, okay, because we have to take into account certain eventualities. Okay, so what are the one eventuality is that the page may have no links, right? So I go to a page and it's over here, and then it has no egress link. So you could model it as a self loop, but then you get an absorbing state. So if you ever reach the state, you never leave. Okay, but that's not true. That's not true. You go to a page that has no links. What do? You kind of stop, and then you're going to some other page, right? So let's say there are n pages. Okay, then what we can say is we come over here, we're going to go out to any of them with probability 1 over n. So it's 1 over 10 to the 11, right? It's a very small number, but nevertheless it's a non-zero number. I'm just going to visit some random page, okay? So we can say that. The other thing is that when you come to a page, you may choose not to follow a link. You may choose to go to some random page anyway. So what we do is that if a page I has k links, we have a special control parameter alpha. So we say that with probability alpha, we go to one of the k pages, okay? And then with probability 1 minus alpha, we go to one of the 1 minus alpha over n. We basically go to one of those n pages. Okay, that's basically how we do it. Or more precisely, I should probably use my notes here and tell you that the probability of going to I to J, okay, so k links, Pij is given by if link from I to j, then alpha by n plus 1 minus alpha over k. So alpha is sort of the probability that I'm going to not click on a link, and if no link, then alpha over n. And if you do this, then we have this sort of teleportation model. You go from one page, there's no link, you go there anyway with this very small probability. And we can show that this Pij is a right stochastic matrix. And if it's a right stochastic matrix, the power method is going to give us the dominant eigenvector. And when you do that, you basically are going to get the stationary probability distribution, and that gives us the rank ordering. Now, this is the origin of Google. So in 1996 or 97, there was a tech report published. Interestingly, the Pagerank algorithm was developed by Larry Page. So maybe he called it after himself, but Page and Brin, and I think Motwani were the three authors. And it's a tech report from Stanford, which said, yeah, you know, we can treat this whole thing as a stochastic matrix and compute the eigenvector. And why don't we try doing it? And that was sort of the Google.Stanford.edu, the website that was a baby Google. And it worked very well indeed. Now, what they have done subsequently is to actually change this. And instead of using these 1 over k as the weight over here, okay, they actually are using the text around the link to figure out what the link means. So it's not the case that I'm going to just use 1 over k, you know, have links going to different places. I'm going to use the text. And so we're looking at some kind of similarity index between the text and then the link to determine where to go. And also, I haven't told you how we figure out all the pages with the word eigenvalue in it in the first place, right? This is just a rank ordering once you figure out what that is. And this is based on what's called the SMART algorithm. And that was some work done at Cornell University by a guy called Selton. I forget the last name. But the SMART algorithm, it gives you the text search, and then the PageRank algorithm gives you the rank ordering. And together, they first find all the pages, then they find the rank ordering, and then they show it to you in that rank ordering. What goes on inside Google, nobody knows, but this is the published work that we have. And as you can see, it's a straightforward application, at least at the first cut of the power method. The reason why it becomes very hard is this thing over here. Okay, so so we had to do some sparse matrix computation and some fairly complicated mathematics, which I don't know, but there are people who specialize in sparse matrices, and Professor Gene Golub at Stanford, apparently, the story I heard was that the most money ever made consulting was to apply his understanding of sparse matrices to the Google problems. They paid him a lot of money for that, so he doesn't need to work anymore, I guess. Okay, that's all we have. Next Monday, we'll start on transforms.